Welcome friends. This is my new YouTube channel where I am actually delivering lectures on some important topics of geography related to CBCS syllabus, and I am going to present my third topic today that is very important from the point of view of geography. First of all, we know that we are running through the hard time where the whole human civilization has been greatly threatened by a small microscopic element. We know that harmful element is called as the novel coronavirus. We previously didn't do that particular type of fight against viruses on a very large scale, on a global scale. But this is really a hard time. Although we are the teachers, we have the duty to perform, and as well as it is my basic aim to rejuvenate the wisdom of knowledge of the students during this hard time of lockdown. I know that they are to some extent sluggish, they become to some extent sluggish nowadays because no schools, no colleges and no university classes are regularly going on. So this is the only way how we can represent so many relevant topics from our subject, and we can learn so many new things. So my today's topic is on transport network analysis using modern application. This particular part actually covers a small practical portion of 4th semester CBCS syllabus. And as we know that any kind of society, any kind of geographical setup, it is truly complex, as because it is composed of so many animate and inanimate objects. And we know that these animate and inanimate objects, they are depending on each other to form a habitat, to form a society, to form a geographical landscape. So over this, a very invisible flow of interaction between those elements is going on. So as a geographer, it is our basic aim, it is our basic objective to know that ongoing process that develops a beautiful structure of dependency. So in mathematics, we know that there is a term, there is a very important term is there that is called as topology. Now, what do we mean by topology? It is a beautiful geometrical shape of any object or any interrelated objects. But the thing is like that whenever the object or objects are having a phase of, are having experiencing kind of transformations, but their geometric property will remain same. This particular type of discussions highlighted in the branch of topology. The geometry or geometrical elements or properties remain same, although they are having a kind of transformations that is rapid or slow. And as well as in network analysis, we know that we are talking about the form of a geographical spectrum. We may divide the geographical landscape into small, into medium or into large parts, but scale-wise study is very much important for network analysis, because whenever we are moving towards the large scale properties, we will get the micro elements, and this particular micro elements or objects, they beautifully spread it over the geographical surface and their distribution, and the variety of their distributional pattern comes under the part in geography that is called as the spatial analysis. We know that spatial data is there and a spatial data or attribute is there. A spatial attribute, we know that it is kind of some string values. The number of any hotel room, we can call it as a spatial data or attribute. But any kind of object which has a geographical coordinate, a geographical identity, that may be considered, that should be considered as the spatial data. So in geography, what we analyze, that all is related with the analysis of spatiotemporal variability. So in transport network analysis, our basic aim will be pivoted on knowing the configuration of the spatial network structure, and after the analysis, what are the results we get that will show the behavior of that particular spatial objects. So now we are going to talk about the objective of this particular study, transport network analysis. In society, it is very much important to know about the social interaction between animate and inanimate objects. So whenever we want to know that particular type of interlinkages, interrelationship between so many objects that is sporadically distributed over the surface, in that particular time we unknowingly constructing a kind of complex network. That is the manifestation of that particular type of interaction which is going on continuously. So our first objective is that to use the graph theory, which allows us to understand how objects covering the surface and how they are interacting. Now here we find out one term that is called as graph. Whatever is real, that is called as network. So the mode of the network should be much more complex. But when we are collecting some attributes by means of some points or lines or polygons from a complex network, and we are simplifying it on our flat piece of paper, that will be our graph. Over the graph or on the graph, we can do so many interactive analysis, but it is very difficult to deal with the network. So simplification is very important. Number two, what the implications they have on the spatial organization. This is the thing we just want to know. So what we mean by spatial organization? Whenever we are considering so many spatial and aspatial objects over a piece of land, whenever we are combining or collecting or compiling information from those animate or inanimate points distributed over the ground surface, that will give us a kind of structure. That structure will come up as a graph, and graph is the useful tool for the final further analysis. Now, what are the methods we are going to deal with? Two methods we are basically going to deal with. One is the connectivity analysis. So there must be some linkages, there must be some relationship between the objects distributed over the ground surface. So what is the mode or nature of that particular relationship between those objects? That particular thing will come under the analysis of connectivity measures. Second thing, we just want to know the accessibility measures. We know that in transportation geography it is very much important to mobilize goods, goods, flow of raw materials and other things, as well as the flow of workers also, flow of capital also. It should be supported by some fast transport communication routes, basically the transportation routes or lines. So we want to know that if I want to transport a particular object from place A to place B, should I have transportation route? If the answer is yes, we have transportation routes. The next question come up that is the route accessible for the transportation? Is there exist any kind of geographical obstructions or hindrances? If no, so the movement of the flow will be much more smoother. But if yes, we have to choose another bulk point. We have to change the mode of transportation from that particular point. So whenever the structure is forming after combining point, lines and polygons, it is very much important to know the trend of mobility or the nature of mobility of various goods, manufactured goods, raw materials, working force, capital. Either these particular things are moving easily through these particular nodes or not. This is the basic thing, we just want to know that. Now comes the important question, why connectivity? Simple answer we cited here. To compare the structural complexity of the network, and we need measurements that allow us to describe the degree of network connectivity. First thing is that we have to know about the structural connectivity. Now, if we consider so many links, so many nodes, and the formation of so many polygons, that is contained, one polygon is contained within the area of another polygon, that will make the scenario to some extent complex. So whenever the trend of mobility or the nature of mobility or the inflow of any object is increasing by its magnitude, the structure of the network is getting much more complex. So to know the complexity of that particular network, by considering all the elements of that particular network or graph, we should proceed. Now, where does it fail? The application of graph theory is not suitable everywhere. It has some limitations. One limitation we are going to cite for the students here. By measuring graph theoretic connectivity, we only can evaluate the degree of network structure changes, but we cannot identify what individually has changed on the network. So we can deal with the whole thing, the structure of the whole network. But whenever we are considering the element-wise study, it becomes very difficult. The change of any kind of point or the erasing of any kind of point, is it going to create any kind of effect within the whole network? Or if I erase one transportation route from the network, is it going to create any impact on the overall network structure? So this is the vital thing we have to know. Otherwise, this particular type of analysis is very much suitable for the overall analysis of the overall structure of the network. But if we come to the study to element-wise description, that will be much more difficult. Now the question arises, why accessibility? I have discussed little bit. Now, whenever we are considering one network, it is consisting so many nodes or points. And these nodes are very vital to create balance at the center and around the graph or within the graph. So these particular points of balances or nodes should be studied to make our idea clear about the whole graph. So here lies the importance of studying the role of each and every node in the graph to know the nature of accessibility through it. Otherwise, it will be much more difficult. Now, one exclamatory sign has been provided after the conversion. Why conversion is needed? We extracted graph from network. From graph, we can prepare so many metrics so that our analysis will be much more easier. It will be much more conveniencing. What is matrix? Already we know in third semester. It is the array of data that is presented into R into C table. It consists of some rows and some columns. So whenever we are getting that particular type of R into C array, row into column array, that will give us the idea of matrix. Now, so many matrices are there. C matrix is one of the important thing that will judge the direct mode of connection between the node. After that, we have T matrix, where we can judge both the direct and indirect mode of connections between the nodes. D matrix or symbol matrix, I am going to present this particular thing in my topic today. This is very important. This is included in the syllabus. Symbol matrix, that is called as D matrix. Through this, we can find out the shortest possible distance between two nodes or pair of nodes. This is very important. And last one is the L matrix, that gives you the real short distance between any pair of nodes. So among all these four things, we are going to deal with only the symbol matrix or symbol index later on. After that, each and every analysis, it should have a theoretical or mathematical background. Now we know that graph theory is a part of the combinational topology that has a particular language in mathematics, and it is very much useful to know the structures of the network and the elements of a network. Nowadays, not only in mathematics, it is useful in the arenas of social sciences also, especially in geography, especially in transportation geography. Now, that particular type of graph theory should have some functionality. This particular functionality here, I have divided into two parts. First one is that from the analysis of the graph as a combined element, we can derive some single values, and these particular single values will describe the nature of the whole network or the whole graph. This is the one way. And the second way is that the vector of the numbers, which measures the relationship or the direction of the relationship between the individual elements and considering the whole network. So in the second case, we want to know the degree of orientation of the graph elements. So in case of flow analysis in economics or in regional planning, we just want to know that in which direction the capital is flowing on, or in which direction the levers are migrating from one place to another place. So whenever we are talking about the direction and comparing both the small elements and the whole structure of the graph, in that particular time, we are dealing with the embedded vector element of this particular graph theory. Number two, as the networks are the real world spatial systems, so it has so many linkages, and we can say that it is the replica of the real world scenario. So in graph, we are simplifying the complexities of the network whenever we are converting the network into graph. Number 3, there are some basic parameters of the graph. We can divide these particular parameters into 3. One is subgraphs. I will later on discuss later on. Number 2, edges or branches or linkages. In GIS, we can call it as lines, and vertices. Obviously, it is called as nodes. And in GIS analysis, we know it as point. What is the structure of a graph theory? Whenever we are talking about the overall layout of the network, that is called as the structure of the graph theory, comprising all the small elements, that is point, lines and polygons. But it is not necessary that all the graphs will be comprised of points, lines and polygons. It may be closed type, it may be open type, so many things may appear. Number 5, basic graph theoretic measures imply 2 things. One is the structure of the graph, I have already discussed, and now comes the efficiency of the graph. Now this particular term, efficiency or the working role of a particular graph, is dependent on 2 things. That is the connectivity. Either the graph is connected by the nodes in a proper way or it is not. And as well as number 2 is the accessibility. So the flow of any kind of currency, any kind of human being, any kind of labors, any kind of capitals, any kind of raw materials, either it is going on freely without creating any obstructions in front of it. So efficiency depends on 2 things. One is called as accessibility, another is called as the connectivity of the graph. In our next slide, we actually presented here one beautiful shape of a graph. It is a graph. It is taken as a replica from the real world complex network, and whenever it is plotted on a 2D plane with the basic elements, one is node, another is vertex, it becomes a graph. So this is a graph, this is not a network. Now we can observe here P, Q, R, S, these are the vertexes or nodes. And if we talk about the edges, we can say that PQ, QR, RS and SP and as well as QS, these things are called as edges or linkages. Fine. Here we can find out a distinct difference from the previous graph. Here some directions are showing, and this particular type of directions gives this particular graph a to some extent different type of nature. First one is called as undirected graph. Direction is not specified. And in case of the second one, whenever we provided the direction along the linkages through the nodes, it becomes a directed graph. Now we calculated number of node or vertexes equals to 4, P, Q, R and S, and number of edges or branches 6. You can easily calculate P, Q, QR, RS, SP and QS. Now it is to some extent different, that is node pair. 2 elements are combining to create one pair. It is a very easy concept. So PQ is a node pair, QR is a node pair, RS is a node pair, and SQ is a node pair, and QS is a node pair. Fine. After that, it is very important to talk about the degree of the nodes within a graph. Capital D is actually signifying the degree of nodes. So, in case of degree of node, this concept is very important in graph analysis, and we can say that in case of point Q, there is only one incoming linkage or branch, that is PQ. This one, only one. Sorry, in case of P, sorry, this one, I was to some extent wrongly describing P for Q. If we look at this P particular vertex called as P, here we can find out that two incoming linkages or branches are coming towards the point P. So it's the degree of the node is 2. In case of Q, one branch is incoming, another is outgoing. So here the degree is only 1. In case of point R, only one incoming branch, that is QR, is moving towards point R. So the degree is 1. And again, if we consider this particular vertex on node S, one incoming branch is RS and another incoming branch is QS. So its degree of node, the degree of the node of S is 2. So whenever we are summing up all these values of individual values of degrees of nodes, it will give us 6. And 6 equals to the number of branches or edges in a particular graph. So by mathematical rule, it is constant. So the total degree of nodes in a graph, that should be equal to the number of branches in a graph. The same thing we find here in our next slide. Another form of graph is given here, but the nomenclatures are same and the directions are same. And the second one is to some extent different. Where lies the difference? Here we actually provided another branch. Along this, adjusting these two nodes S and P. Previously it was not there. So where lies the basic difference, we can easily identify from here. Now here comes the concept of incomplete graph. Previously what we described, that was complete graph. Now both of these graphs are incomplete graph. So what is the concept of a complete graph? In case of a complete graph, each node pair having one branch or line segment, it should not be 0. If I elaborate, previously we know that there was a branch between Q and S, but here that particular branch is removed. So in Q and S there is no branch, no linkage. So it becomes a kind of incomplete graph. And again in the second picture we can say that between S and P, previously one branch was there and here we added another branch. So it is exceeding the value of 1. So by logic or by rule, this graph is an incomplete graph. This is not a complete graph, because in case of a complete graph, each node pair there will be only one linkage or one edge or one branch. It should not be 0 also. Fine. Next, another type of thing we presented here. We discussed about complete graph and incomplete graph. Now we are going to talk about connected graph and unconnected graph. Here we presented, this is a connected graph, but whenever we actually reduced two branches that were previously holding this point C, when we actually erased these two branches BC and CD, this point becomes isolated. And whenever there is a presence of isolated point in a graph, that is called as a unconnected graph. So we can say that by logic, every type of complete graph, it should be a connected graph. But all the connected graphs should not be complete graph. Again, I am repeating, all complete graphs should be connected graphs, but all connected graphs should not be complete graph. For example, this is a connected graph. There is no such isolated vertices are present here or is present here. It is a connected graph, but it is not a complete graph. It is an incomplete graph because this node pair S and P, it is having more than one branches. One is here and another is here. So it is incomplete graph, but it is connected graph. Next, there are some simple graphs on the screen here I presented. First one, we can call it as subgraph. Now, what is the concept of subgraph? Because while deriving cyclomatic number, it is very important to know the concept of subgraph. Now, in case of a subgraph, we know that less number of branches compared to original graph. If previously, if we consider this graph, here the number of branches 1, 2, 3, 4 and this oblique or diagonal 5. If we remove at least one branch from this particular graph, suppose I am removing one branch BC, fine. So it will become a subgraph. If I remove another branch, that is CD, it will again become a subgraph. So compared to the original graph, in a subgraph there will be a less number of, at least one less number of branches. In our second graph and third graph, what we find here, that is called a spanning subgraph. Now subgraph and special type of subgraph is called a spanning subgraph. What is called as spanning subgraph? Whenever there is at least one in case of a spanning subgraph, it will retain all the vertices that was kept in the original graph. Previously, here we find from the original graph 4 vertices are there. In this graph, we able to retain 4 vertices, so it is a spanning subgraph. And again here we able to retain 4 vertices. So compared to the original graph, if we retain same amount of vertices, that will be called as spanning subgraph. But this is not a spanning subgraph. This is only a subgraph because it is composed of only 3 vertices. One is less, so it is only a subgraph. So in our next graph, I want to show what is the concept of a planar graph. These two types of graphs are called as planar graphs. In case of planar graphs, there will be no such intermediate branches that will be crossing each other or intersecting each other. It will be a simple form of graph, and our today's discussion will be pivoted on this particular planar graph, concept of planar graph. There is no such interactions, there will be no such intersection of branches in a particular graph. That is called as a concept of planar graph. So here, if we consider all the branches, any kind of intersection we can't observe in both the cases. So it is called as a planar graph. As I told, its edges intersect only at endpoints, not at the middle points. So if we compare this particular branch QR, this particular QR is intersecting with vertex R at the end and Q at the another end. So there is no intersection at the middle of this particular branch or edge. So it is called as a planar graph. So next one is the concept of non-planar graph. It is a complex real world form of a network where so many intermediate intersections can be observed in this particular graph, and that particular type of non-planar graph cannot be plotted on a flat piece of paper. It is very much suitable to draw on the spherical surfaces or curved surfaces. So let's check what is the concept of non-planar graph to memorize. As I told, it cannot be drawn on a plane, and no vertex lies at the intersection of at least two edges. So there is no vertex. It is intersecting, these lines are intersecting, but there is no vertex. There is no vertex. There is no vertex. There is no intermediate vertexes at the points of the intersections. So this particular type of graphs are called as non-planar graphs. Now, what should be the flow of our discussion? According to the syllabus, our discussion will be highlighted basically two things, that is the degree of connectivity and the degree of nodal accessibility. And under the tree of degree of connectivity, so many things are there: link node analysis, spatial structural analysis, efficiency of edges and vertices, diameter of a graph, and density of a graph. All these things we are going to check except the spatial structure of the graph. Under the link node analysis, we can get three indexes, alpha, beta and gamma, and cyclomatic number is very much useful while deriving the value of alpha index. So this particular three indexes, including cyclomatic number, is very important in transport network analysis, and they provide very logical inferences after the analysis. And from eta, theta and pi index, these three indexes are very much important to know the structural configuration of the edges and vertices, but without temporal comparison we can't come up with a very sound or logical result in case of eta, theta and pi index analysis. We need to compare the temporal results, otherwise we can't comment very logically on the results. The last one is the degree of nodal accessibility. Under this we are going to discuss only the symbol index. As we know that the symbol index is the straight line or shortest possible straight line distance between two furthest points or furthest nodes. And whenever we try to find out this simple straight line roots with the help of a matrix, the analysis becomes much more convenient. As I told that we are dealing with a planar network or planar graph, which is in reality to some extent less complex than a non-planar graph. So our whole discussion will be pivoted on dealing with a planar graph, and number of formulas are given here for the analysis of planar graph. First one is the alpha index, which is the most important one, and actually the numerator part in the alpha index presented by cyclomatic number. Small e represents the number of edges or linkages, and small v represents the number of vertices or nodes. And here the capital G is the number of subgraph. As I told that subgraph is just a subset or small part of a large graph, so that if we provide an example that we are considering the transport network of only Darjeeling district, which is just a subset of the whole transport network system of the West Bengal. So it should be considered then as one. In most of the cases in examination hall also, whatever data will be given, the students should be considered the capital G or number of subgraph as one. Alpha index is also called as redundancy index because it actually reduces the poor functioning of the previous index and incorporate some new logical ways to rule out those problems. And alpha index value ranges between 0 to 1. 0 means minimum connected network and 1 means maximum connected network. After that, the beta index or Betti index, it is a simple arc node ratio derived by Kansky back in 1963, and it should be less than 1 and should be greater than 1. And what are the meanings come out from the analysis? That is, if it is less than 1, so we can say that large branches without circuits. If it is 1, that represents a complete circuit, and if it is greater than 1, it represents more than one complete circuit. Here we know that a planar graph can be subdivided into number of closed circuit or closed parts of the graph, so that in that way we can interpret. In case of gamma index, which is also derived by Kansky in 1963, and the value ranges between 0 to 1, here the gamma index actually represents a ratio between observed number of edges to the maximum number of edges in a planar graph. 0 means number of edges increases, that indicates a complex network, and 1 means number of edges decreases, that means a very ill-connected network or poor network connectivity exists. Eta, theta and pi index, these particular three things should be comparable on a temporal scale, because the value of one particular temporal scale is not logical to come up with a interpretation. If we consider two temporal scales like the transport network connectivity of Darjeeling district in 2001 and 2011, so after the comparison we can come up with logical interpretation. Otherwise, the low value in case of eta and theta index, it indicates the high network accessibility by mode of vertices in case of eta index, and in case of theta index the maximum accessibility of the whole network can be presented from low value of this particular index. Now in case of pi index, which is a kind of circular fit of the whole graph within a circle, it indicates the span of the whole network and which has very keen correspondence with the diameter of a network. And in case of pi index, the low value indicates the ill-connected network. In case of rugged hilly terrain, the low value can be achieved in case of discussing about pi index. But in case of diameter of a network, which indicates the spread of the network or span of the network, the dij represents ij here considered as two most distance points. If we connect these two distal points with the help of a straight line, we can get a particular diameter. And from that diameter, if we half the diameter, we will get the radius, and so that we can draw a circle to fit the whole network within that particular circle. And density of the network obviously represent that high value. If we get high value, we can say that this particular type of increasing density of a network represents increasing connectivity and accessibility. In most of the cases, this particular type of density is very high in flat terrains compared to the rugged terrains. So if we consider Coach Bihar district, if we consider Uttar Dinajpur, Dakhin Dinajpur district, so that the density of the network, even in case of Kolkata district also, the density of the network per square kilometer, within per square kilometer area, it should be much more higher. In case of Detour index, which is a very important topic to be considered, derived by Kansky in 1963, it represents the actual distance in SI unit between two vertices and the straight line distance to the same points. So the high value of the Detour index actually representing the low efficiency of the network. I previously told that the efficiency of the network can be considered by means of its connectivity and by means of its accessibility. So both the things can be portrayed by analyzing this single Detour index. Another type of index is there which has close similarity with the Detour index, that is called as vertex Detour index. But while deriving vertex Detour index, we have to take the help of the symbol matrix. Without using the symbol matrix, we can't derive the vertex Detour index. So there exists to some extent difference between the vertex Detour index and Detour index. After that, we would like to talk about the performance trio. This is a very important part of our analysis and how we have done our whole analysis. This particular trio will make clear the whole thing. Now first is the use of the Google Earth, that is to know how to extract the spatial information from this Google Earth platform. We can easily extract point, lines and polygons, this particular type of vector features which is carrying spatial information tags within itself from Google Earth platform in form of KMZ or KML file using GIS. It is very much useful while using in other GIS platforms. The second one is the Global Mapper GIS environment. Here we can create so many vector layers, that is point like nodes, lines means branches or edges, and we can do that, we can attribute so many datas within each points for the ultimate preparation of the vertex Detour index. After that, there is another tool which is a very popular one, that is the ArcGIS environment. This particular environment has been used for performing the interpolation by using IDW interpolation technique, and the final layout has been done over here. But if we look back, when we didn't have that particular type of GIS facilities. During that time, using topographical maps and other maps, this particular instrument called as opisometer is very much useful to derive the lengths of the edges contained between two vertices. So in case of the UG students, they are having less chance to use those sophisticated techniques, so that in their fourth semester they should deal with opisometer to carry out the whole analysis. So here we start our analysis using the first platform, that is called as Google Earth. As we know that it is a very popular GIS platform around the world, and it is using Landsat data, and DEM informations are embedded within this Landsat image. So we can use this particular view or data as raster data. Now our task is that over the raster data we have to create vector layers by means of three things. One is point, that is called as node, another is line, that is called as edge or linkages, and another thing is called as the area. So here the area is the administrative boundary of the Darjeeling district, and we actually digitize the roads with the help of this particular ruler. We actually used here the path, and using this particular path tool we traces on the roads accordingly. And before that, one thing I just want to make you clear that while starting the digitization you have to active this layer that is called as roads. Whenever you are activating this particular layer, you will get the complex connection of so many roads. So this particular view is a kind of real network. This is not a graph. And after that, using this particular tool that is called as add place mark, we can provide so many pins, particularly at the junction points. And we will use these particular pins as vertexes in our further analysis. So this particular tool has been used to extract the spatial information by means of point, line and polygon, and we actually saved all this information in KMZ file. We export this particular data files into global mapper. So now our task is to carry out our further discussion with another GIS tool that is called as global mapper. So students, this is another GIS platform called as global mapper. It is also a popular one. Blue Marble Geographies, they actually developed this particular platform. So after importing all those KMZ file in this particular window, we can get that a real graph is ready here. This particular type of graph can be drawn on a flat piece of paper on a 2D plane. So this particular thing is the administrative boundary of the Darjeeling, and the intermediate lines are called as the edges contained between so many nodes. Now previously it comes as at place mark pin, but now it has been converted into nodes or vertexes. And the names of the real world places provided here, it starts from Khoribari, and Darjeeling town is here, Mirik town is here, Karshiang is here, and this is Shiv Mandir, the NBU campus, North Bengal University campus, and this is Darjeeling Mode. All these particular places, we know that these are the very familiar places. So now our task is to convert this particular nodes by providing logical names. Our task is now is to provide logical names to all this particular node. So here we can easily identify the transformation or the change. Previously these nodes were identifiable by means of their real world names. Now it has been categorized or marked as by providing alphabet identity and from A to Z, and after that 1 to 11 Arabic numerics we used here. So this is how we actually prepare our graph from a real world network. So this is the graph. This can be carried out. This can be taken with us for our further analysis. So one important thing I just want to show that how to create polygon, because this is the administrative boundary, this is just a line. So we need to show this particular area of the Darjeeling district, the old Darjeeling district, better to say, it becomes now a area feature. So three things we have: point features, that is called as vertex; line features, that is called as edges; and this is called as polygon. So three things we have get. After that, we need to know one thing, that is the diameter of this particular graph. Now if we look this particular graph very closely, this 4 vertex, and if we move towards down, this 7 vertex, these are actually lying far away from each other. So by connecting this particular lines, by connecting these particular points with the help of a line, we can easily identify the total length. The total length is given below, that is 88.65 kilometer. Now this can be considered as the span of the network or the diameter of the network. So if we consider the half of this, that is 44.4 kilometer, this part, that will serve as the radius of a fitted circle. So now if we consider this particular diameter or radius of 44.4 kilometer, we can draw a circle. We have to choose a middlemost part in this particular graph. After that, here you have to provide the value, that is the range of the radius. 44.4, we derive the value and just click OK, and it will come up as a circle, and we can say that this whole graph has been suitably fitted within this particular circle. So this is how we can do some analysis with the help of this sophisticated GIS tool. We again come back to our main PPT, and sorry, we are moving to some extent back. So this is not the right path. So we have finally come back to our main slide, and this is the real world scenario taken from Google Earth image, Google Earth platform image, that is called as the Landsat image. So this is the real world complex network, and we have converted this particular network into the form of a graph, and this particular type of beautiful network has been presented with the help of ArcGIS platform, and we considered this particular graph as planar graph for our calculational convenience, because in examination there is a rare chance that we can get a non-planar graph. So we considered it this graph as a planar graph. So after that, we should talk about some results now. Now we get the result of the alpha value, that is very less, that means very close to 0. Now in case of alpha value, alpha index, whenever it is very much less, we can say that it represents a minimum connected network. As we know that some northern parts of the Darjeeling district comes under the hilly and rugged terrain. So it is unable to create the complexity in the northern part. So that's why we can say that the alpha index value is to some extent less. So cyclomatic number used in alpha index calculation, that is 0.5, we considered subgraph here as 1. So beta index ranges between, it is not really ranges between 0 to 1. It may fall below 1 and may exceed than 1. So in that case, the value of 1.10 exceeding 1, so we can say that it is representing a kind of complete circuit or complete graph having more than one complete circuit. So we can say that by means of this particular beta index, it indicates a better amount of connectivity within the network. This gamma index value is actually showing a less amount of value, that is 0.39 only, and as it is staying away from 1, so that we can say that the number of edges are increasing. So gamma index is actually, whenever it is moving towards 1 or exactly 1, we can say that the number of edges decreases. But whenever it is moving away from 1 towards 0, we can say that the number of edges increases. So it obviously indicates that it is to some extent increasing the complexity within the network, as well as it is increasing the amount of connectivity within the graph. The eta index and theta index, by their configuration, they looks like to some extent same, but there is a difference in the denominator attribute. In both the cases, we can't comment a particular thing from these two values of eta index and theta index, because proper amount of comparison is needed between two time scales. After that, the pi index is actually indicating either the network is ill connected or it is well connected. So whenever we can compare between two time scales, we can say that the nature of its connectivity, either it is representing a good connectivity or it is lacking behind by means of a good connectivity. Diameter of the network I have shown during the time of GIS calculation, and as well as the last one is the density of the network. And this particular density of the network value, it represents that what amount of road length has been contained within 1 kilometer square area. So whenever the density is increasing, we can say that the chance of getting complex network becomes higher and the connectivity becomes much more complex. So in that way, we can discuss about so many parameters. So we just want to show some statistics on graph element during our calculation. We have calculated total 39 vertices, total 43 edges. Subgraph was considered as 1. Total length of the edges 420.86 kilometer, and the total area of the graph 3158.1 square kilometer. And the maximum distance I have already shown that how did we calculate the figure 88.7. So this is how we actually get some logical statistics, some correct statistics after analyzing a graph. If we again come back to the GIS platform global mapper, I can show that how did I calculate all these particular parameters. Simply choose this particular information I button. If we click here between the edges, you will get that one dialog box is opening, and this particular box is carrying the information featured. So here from we can easily identify the length of this particular branch, and the number of the vertices can be easily identified from the OpenEye calculation. And if we talk about the area of this we can talk about the area of this, area of this particular Darjeeling district. We can easily find out the enclosed area is 3158.1 square kilometer. So this is how we can derive the important graph elements from GIS platform. So now, whenever the thing is like that, we don't have the support of GIS platform. We have to use opisometer. So how we should carry out our calculation? I just want to show the same thing in an Excel sheet. We have arrived in Microsoft Excel, and first part here you should concentrate. With the help of a opisometer, if we run the opisometer along the sinuous edges contained between two nodes, the clock of the opisometer, it should be moved, or the bar of the opisometer, it will be moved towards anti-clockwise direction, and we will get the count in centimeter unit. Keep in mind, we will get the value in centimeter from opisometer, and the opisometer should be run in a clockwise direction. Okay, we get, suppose this particular values 30, 25 centimeter, 40 and 27 centimeters. Now our task is that we have to convert this particular centimeter, we have convert this particular centimeter unit according to the scale. Suppose the map scale is given 1 centimeter to 500 meter. So we have right here the 500, 500, all these particular things are scales. Now if we transfer this centimeter value, convert this centimeter value in meter, we'll get easily that 30 centimeter is equivalent to 15,000 meters, and it is obviously equivalent to 15 kilometers. Simple mathematics. So in that way we can use the opisometer, and we have to prepare this particular type of logbook or data sheet, and we have to find out first the sinuous distance or actual distance, and after that we have to find out the straight line distance. Straight line distance can be measured with the help of a simple linear scale, but while deriving the actual distance, that means this column, we have to use one opisometer. Okay, after that we have collected all these particular values in kilometers, and we go for the analysis of Detour index calculation. Detour index is nothing but the ratio between the actual distance to straight line distance. So if we divide 16.95 with 15.69, we can easily get Detour index value. So after that, if we multiply the DI index value with 100, we will get the value in percentage. So in that way we have done our calculation. We have again come back to our main PowerPoint presentation. This is another slide where we have provided the data of the calculation of the Detour index values, and after that we have prepared a similar type of table where we provided some interpretation clues. Okay, so this is very important for the students. Now in case of alpha index, as it is very minimum, it indicates a minimum connected network. In case of cyclomatic number, no interpretation is needed indeed. In case of beta index, the value of 1.1 indicates more than one complete circuit is present in the network. So it indicates the maturity of the networks, and whenever the beta index is rising, it indicates that the number of complete circuit within a graph is also increasing. From gamma index, the network, we derive the value 0.39. We can say that the network has reasonable number of connectivity. Basically this particular connectivity depends on topographical function also, that reflects in Detour index. Eta index, theta index, And pi index, although we have derived the values and I have shown how to calculate the values, but temporal comparison is needed. We have to consider 2 years. Otherwise, it will not be possible to come up with a interpretation or inference. So diameter of the network, that represents the span of the network, how much it is spreaded and how well it is the graph is fitted within a circle. And the density of the network represents the complexity of a particular network having so many road connectivities. Here in case of our calculation, 1 square kilometer area holds the length of 130 meter of road lengths. From Detour index analysis, we found that almost all the values is exceeding 1. That means exceeding 100 in percentage. So whenever the value of Detour index is increasing, that indicates low efficiency of the network. And low efficiency means lesser the directness of the route from a given vertex to another. So it is as well as lessening the better orientation of the graph. Whenever there is a higher Detour index value, the orientation of the graph, it is somehow been obstructed, and as well as the connectivity and accessibility also greatly hampered or reduced. So this is the contour map of the Detour index. These dotted lines are representing that how we can divide this particular area into number of zones. Basically we have divided into 5 zones. In ArcGIS we have taken the help of IDW interpolation technique, and we finally able to derive this final output map. Here we can say that the middle part of this graph having low network efficiency by means of high Detour index. But if we move towards lower part, that is Bagdogra and Hashidawa and Shiv Mandir area, almost a flat area, here the efficiency of the network is very high as the value of the Detour index is less. But whenever the thing is like that, we don't have the support of GIS platform. In that case, I will suggest the student to arrange the data, find out the highest value and lowest value, and in the same way as you generate the frequency table in 3rd semester while doing statistics, you follow the same process. Number of classes can be derived by using Sturges formula, and class width can be find out by using this formula. So after that you can find out the logical number of classes and their widths. So in that way you can also divide a particular area into number of zones. Okay, here I actually presented 4 classes. The low value of Detour index indicating high network efficiency, and high value of Detour index indicating low network efficiency. So here the contour intervals actually presented. After that, the last part we have to talk about the symbol distance matrix. From here we can identify that this is a planar graph. Although this is a incomplete graph, because this particular node pair C and F, they have 2 connectivities, 2 linkages, so it is a incomplete graph. So in this incomplete planar graph, we can say that how to calculate the symbol matrix. All the node attributes can be arranged row wise, and along this column the same thing should be repeated. So we have to find out the shortest possible routes to move from one node to another node. So from A to A, it is not possible to move. From A to B, if we move from A to B, we have to cover only 1 linkage. Similarly, if we move from A to C, we have to cover 2 linkages, that is AB and AC, that's why it is 2. Here the 2 is marked in red. Why it is so? Let's check. We have to consider B and F distance. Okay, B and F. So if we want to move from B to F, this particular route we have to follow, BA and AF. That's why this is written as 2. Always keep in mind we have to find out the shortest possible route. We can't spare our time, we can't spare our extra amount of money. So shortest route we have to find for the better accessibility. So why it is 3 marked in red? So we have to find out CG connectivity. From C we have to go to G. So we can move from CD, after that we can go to DF, after that we can come back to FG. So in that way I presented the symbol distance matrix. After that another matrix has been presented where the straight line distances and grey colored actual or real world distances has been superimposed on the graph. So while deriving the vertex detour index, we have to consider two things. One is the actual distance we have to measure. Here the actual distance is shown in grey line, and we have to consider the straight line or the shortest possible path. Now let's check how this particular matrix has been prepared. Suppose why it is written as 1 plus 1 plus 1, for example, from A to D. We just want to move from A to D. If we want to move from A to D, we have to cover AB having 1 kilometer of length. After that we have to cover BC 1 kilometer length, and we have to cover CD 1 kilometer of length, so that it is in total 3 kilometers. After that, if we check this particular box that's representing how we can move from C to G. Okay, C to G. Two possibilities are there. We can move clockwise or we can move anti-clockwise. If we move clockwise, we have to cover CD, that is 1. After that, DF, that is 3. After that, FG, that is 2. So we can get the value of 6. But if we move in anti-clockwise direction, we have to move through CB, that is 1, BA, that is 1, and AG, that is 1. So again, if we sum up, we will get the value of 6 same. So in the way, we have to calculate the row-wise totals. Okay. Here the row-wise totals is taken for the straight line distances. Now check. This is the actual distance and the straight line distance I talked about. Now what is the formula of vertex detour index? The row total of the actual distance. I didn't calculate the actual distance, which is shown by the gray line, but I calculated the row total of the straight line distance. So all this particular 17, 16, 16, 15 up to 28, all these particular things indicates how to calculate the row total. So there exists a keen difference between calculating detour index and vertex detour index. So in the same way, after that we can go for the interpolation. Okay. So hope you enjoy this particular video and you have learned so many things. Please do subscribe my channel. If you need any kind of raw documents or raw files, you can contact me through my mail. Stay safe, stay home, and my best wishes with you. Please go through this video very carefully for your better preparation. So thank you so much.